All right, welcome to chapter 14. This is, I think, an exciting chapter. We get to do convolutional neural networks and start image processing and see some interesting applications of neural networks. I am again recording this from my attic at home, and I again have a cat on my lap, so you may hear her meow, but it is still we're still trying to maintain social distancing, and the campus is still closed. So, okay, let's start by looking at the textbook here. This introduces convolutional neural networks and again looks at kind of the biological component of this, particularly the visual cortex and how the visual cortex was or has been explored. And there's some really interesting work. If you've never read some of the uh, biographies of this work, it's really quite interesting. Nobel Prize was awarded for some of this work here. Unfortunately, this is not a neuroscience course, so we won't go into too much detail in here. And the book does an okay job of describing this work. Let me jump here. So in our notebook this week, again, we'll have this first section where we just bring in our libraries and set those up. Um, and then we talk a little bit of, I have a quote here from the book. One thing I do like to show is there's this image from this University of Sussex discussion of visual cortex. So in the back of your brain, so your eyes here, they feed images to the visual cortex of your brain, the back part of their brain here. And there are different sections of the visual cortex here, which are often called different layers, and there are different types of cells at each layer here. And at the first visual cortex layer, V1 it's usually called, we have simple cells, and they usually are just like vertical line detectors. So they will detect if there's a vertical line. It often won't detect if there's a diagonal line and stuff like that. And what this is trying to show is that this is made what's in the visual field here is this bar, and it might be off center or diagonal, and this is the firing rate of the neurons. So when the bar is right in the middle, we get a good firing rate. When this bar is off to the side, we don't get a good firing rate. Same here, no firing and no firing. So the neurons are only active in this one cell. And then we get more complex actions where, like, these cells will only fire or will fire more when the vertical line is moving across the field and stuff like this. But here, this is what I want to show you, is that you have both a red and a right and left eye, and they're mapped different sections of the visual one cortex. And also then there are whole bunches, layers of these neurons. Like, this would be a whole layer of neurons that map to every part of your visual every part of your eye that you can see, your visual field. And this would just be detecting vertical lines. And back here would be a whole nother section of neurons that just be detecting horizontal lines. And each other, slanted lines at different degrees are here. And they've actually mapped these out and found that the visual cortex is like this. You can find the region of the visual cortex where the right eye will only respond to a line at this angle on the field. And again, would be like your whole visual system, what you can see through your eyes here. So each different neurons here will map to different things. So if there is a vertical, or like this case, a vertical line, if there's a vertical line in the upper left hand corner of your visual field, that neuron will fire. So these are whole packages of neurons. And so this largely formed the basis for these convolutional neural networks and how they were set up. So that's why I wanted to show you that image. So we want to look at these convolutional neural networks and how they work and how filters work. And these have been used for a long time. In fact, you often see these applied to images like in programs like Photoshop. So here's an image in Photoshop, and Photoshop has these things called filters, and so I can select one of these filters and like find all the edges, and I'll do edge to end find these. And what it's doing, and so it will do basically what we're going to see. So let's try to figure out how these filters are applied. So here's a picture of this kind of animated GIF, but let's look at some other examples of this example. I like this visualization that's out there of these kernels. So this shows a simple grayscale image on the right, and then the corresponding, each of these grayscale values is a simple value between 0 and 255. So the dark ones will have higher numbers like 250s, and the lighter numbers will have I'm sorry, wrong way around that. The lighter numbers will have higher numbers, and the dark numbers will have lower numbers here. So this might be a 20, this might be a 250 value here. So and this is our images, and then again, this is all blown up, pixelated. This is what it would look like normally. And then we can apply different filters to this. So we can actually select different kinds of filters here. And these will detect different things. And what these are generally, a lot of these filters are 3x3 blocks. And what we'll do is we'll apply those to our image. Here we're going to take this 3x3 block, and it shows up as kind of a red 3x3 on our image here. And what happens is that if this is our filter, the top left pixel value is multiplied by 1, and it's added to the next one down, which is multiplied by 2, and the next one multiplied by 1, and then the next one over to the right is multiplied by 0 and 0 and 0, and the next ones over are multiplied by -1, -2, and -1 again. And so if I position it some places here, we'll get different values, and this shows the different calculations that are being made here. And if I this is actually a vertical line detector. It'll look for a vertical change in color vertically. So if I go over here to where there is a vertical detection here, I will detect that vertical line there. And so you can see the top left pixel is 158, and I'm multiplying that by 1. The next one is 181 down, and then 156, and multiplied each one by 1, by 2, by 1, and then the whole center row is multiplied by 0, and the far right row is multiplied by -1 here. And my result is 243, and then I convert that as if it were a color, a grayscale color. For this, and so that's a bright white. And so you can see the original image is on the left, and then the image after we've applied this filter is on the right as we go. And so now you can actually try out different filters here. I can look at like a blur filter, which will just blur everything, and basically just averages all the values together. And so again, if I look at one of these spots, you can see it averages the cells around it, the 3x3 cells around it. It's interesting, we often do odd numbers, because then if the question is, if you're applying a 3x3 filter, where does that go? So basically what you're doing is you're trying to figure out in the new image, what color should the center pixel be of the 3x3 grid. And so that center pixel is what you're calculating. So when we're calculating here, let's look at another example. Like this, we want to calculate what the updated value of this pixel should be, and so we're going to multiply all this around it to calculate this pixel. I don't know if that makes sense, but again, you can kind of drag this around, and you can see how this filter is applied, hopefully. So to see if you're playing with this and see if that helps you look at these images a little bit. The book also tries to describe this in these convolutional layers actually they talk a little bit about this, and then they talk about these filters, and they talk about like a 7x7 filter or a 3x3 filter, and how these filters are applied here. But again, I think it's hard to visualize, and that's why I like this visualization example here. Here's another example here. This is an image, and then we're applying this filter over and over again to the image. And the filter is kind of a corner detect or an edge detection where we have some ones and some zeros. And so you can see that the image is applied to different sections, and then we fill in. And this subsequent image is actually a little bit smaller than this image because again, we can't apply the filter to this pixel. When we apply it in this corner, and we only get this pixel. So we lose the border. We lose 1 pixel around the whole border when we apply this generally. Okay, so how do we handle that? What if we wanted this image to be the same size? We do something called padding. Padding is where we would add like a set of zeros all the way around the image, or maybe we would here we would average the surrounding pixels, or somehow we would add a padding of 1 or 2 pixels around our image, and then our resulting image, our convoluted image, would be the same size as the original one. And this is what like Photoshop and things like that do. When you apply filter, they automatically pad your image so that your new image is the same size as the original image. Another question is stride. When we apply this filter, how much do we shift our image over for this? I'm gonna go, oops, not that one. I'm gonna go back to this one for a second, talk about make sure we're understanding that. So let's start right by his eye here. So this is the image applied, and now the question is, for the next pixel in my next image, do I move over 1 or do I move over 1, 2? And often you just move over 1, and then the resulting image is the same size basically as your other one. Again, the only question is what happens near the corners. And so this actually does, you can see this actually is doing some padding, so I can move this image all the way up here. We have this thing called the stride, and that's how much we shift the image over. So this is a stride of 1. We're applying the filter and then shifting over 1, applying the filter, shifting over 1 pixel, and applying the filter. And then again, when we go down, we go down a single pixel. But there will be times when we want to do a stride of 2. And with that, we'll apply the filter and then shift over 2 pixels, and then the resulting image will be half the size of the original. And then filters, again, these are the types of the 3x3 or 5x5 or whatever values, and how you're going to do. So like this is called a sharpen filter, this is called a blur filter. This Sobel filter is actually an edge detection filter. This is actually a vertical edge detection filter, and there's different ones. And we used to actually program these all by hand, but nowadays we'll have the computer, the neural network, learn its own filters and apply its own filters. Here we'll just say create a bunch of 3x3 filters and find good values for them, learn good values for those. So I'm going to have you see if you understand this. And again, it's a little bit of bother, but I think that really the best way to do this is to actually do it manually by yourself to show it. So here's I want you to create a copy of this Google Sheet. This is an image. It's supposed to be a peace sign. It looks more like a scary alien, but sorry about that. And again, we have values ranging from 255, which is white, to 0, which is dark black, which I actually have is green here, so you can just still read the numbers here. So this is our original image, and here's our filter. This is kind of an edge detection filter, 1s, 0s, and a -1s here. And so what we'll do is we'll apply this filter to this region initially, and that'll be stored in this pixel value. So we'll take a -1 times 255, 1 times 255, 1 times 255, 1 times 255, and then 0, 0, 0. So anytime I multiply 0, these will all be zeros. And then negative 1 times 255, negative 1 times 255, and then negative 1 times 150. And we'll add those up. So that's what this value here will, well actually, sorry, we'll do that in just a sec. First, I should have read the instructions first. First, we're going to apply a max pooling filter, which simply does a strata 2 and reduces the size of it. So let's talk about what max pooling does. So we're going to look at 2 by 2 grid and just average all those values out for this. Oh, actually not the average, it's called a max pooling, so we're going to take the max of those values. So I'm going to look at these 4 values and find the max. They're all 255, so the value is 255. I'm going to shift over 2 pixels, so over 2 pixels here, and find the max. There's 255 here is a max. I'm going to shift over 2 more pixels, and here the max of those 4 cells is 150 here. So I want you to fill in some more values here. Keep shifting over, see if you can fill in. So this image should be roughly half the size of this image here that you'll get. So see if you can fill in some more of these values. So for example, if we did a 150, we do another one here, this would probably be a 150 also. For us. If you just type in the values, it should color it appropriately for you. Okay, so now we'll have a new image here, and now step 2, going back here, we're going to apply a kernel filter here, 3 by 3 kernel filter. So we're going to do that. And we're just going to ignore the edges for now, and so we're going to apply this filter right up into this area, 3 by 3 area. So we're going to take 1 times 255, 1 times 255, 1 times 200, and then all zeros, 0 times this, 0 times this, 0 times this, and a negative 1 times this row, negative 1 times 150, negative 1 here, and that'll give us our new value here for this. So and again, if our total is less than 0, we'll set the value as 0, and if our value is greater than 255, we'll set to the palette value at 255 for this. So see if you can apply this filter to this value here. So again, when I apply the filter to this area, I get 255 plus 255 plus 200, 0, 0, zeros, and then minus 150 minus, oops, that should be a minus 100 and minus 100. Okay, yes, minus 100, minus 150, and so I end up with 310. But 310 is still greater than my maximum value for images, which is 255. When we do colors, we always do color values between 0 and 255. So I'm just going to put a 255 in there. And then I'm going to shift over, I was doing this, I'm going to shift over just 1 pixel to the right and do this one, and do this calculation here, and get that value, and then shift over 1 more. So see if you can fill in some of these values. And then again, once you get this done, we're going to try to do a 2 by 2 max pooling filter again. Okay, so see if you can do this, answer these questions here. One more, I don't want you to spend a whole lot of time and waste energy, so you don't have to complete the whole image here, just enough so that you can demonstrate your understanding of this and stuff. So just fill in enough pixels so that you can show that, oh yes, I know how to do this calculation. You certainly don't have to do all the pixels. That's not a good worth our efforts. Okay, we're going to actually do this Kaggle digit recognition challenge. This is basically the minced challenge we've seen before. There are 28 by 28 pixels that we're trying to identify. We've seen these images before. I'm not even going to display these images here. We're just going to read these in from this Kaggle challenge. But the Kaggle challenge has them stored in some weird ways, so we do have to do some conversions of these to integers and floats and stuff like that to get this to work. So there's a little more extra work here. Once we get the images in, images, like I say, they are values again usually between 0 and 255, but a neural network likes values between 0 and 1. So we're going to take every pixel and divide it by 255, and so that does it in this case. It's a common thing done with images to divide all the pixels by 255 to get lower images here. We have to do is a little reshaping of these images to get them again in the right format for these convolutional neural networks. I'm not going to go into too much of this, but here we're doing a train test split. We're splitting our data up as we go. And then we're doing one hot encodings for our outputs. So originally the training, like the category number would be 3. But rather than having 3, we're going to encode this as one hot encoding. So we're going to have 10 numbers, 10 zeros or ones. Only one of them is going to be 1. So if the value is 3, the third one, 0, 1, 2, 3. The third one is going to be on, and everyone else is going to be off with these one hot encodings. And again, this two categorical method converts these values into these one hot encodings. So here's our data. And there's a fair amount. So there's 37,000 images that are 28 by 28 pixels. And then for submission, there are 42,000 testing images for us to work with. And again, for the output, there are 37,000 images. And again, there are 10 values wide because we're doing this one hot encoding. There are 10 different categories here. Okay. So let's see how we're doing with the textbook here. Okay, so we've talked a little bit about how these filters are applied. They talk a little bit about like the MINCE data set here. And then convolutional layers. And we'll talk about this in just a sec, how these layers are set up, and we'll have layers of convolutional or filters applied for this and how the filters are applied. And this again is trying to show zero padding and how the filter is moved over, and that this pixel is calculated by applying the filter in this location. This pixel is calculated by moving the filter over, and then this pixel way over here is calculated by moving the filter way over here. And so this filter is applied in multiple places here. And again, here we're working with 3 by 3 filters, but you could imagine this being different size filters, like a 5 by 5 filter or a 7 by 7 filter. Here's a stride of 2 where we're applying the filters, and then we're shifting over 2 pixels, so the stride is 2 each time as we go. And again, they're talking about these filters and applying them in different ways. And we'll often then apply multiple filters at the same time to an image. If you remember our visual cortex picture here, we have all these stacked filters where we have, we'll be doing, basically this is an image, a copy of our image with vertical line detection in place, and this is a copy of our image with horizontal line detection in place. And then we have actually lots of different copies of our image with different orientations of lines. But so rather than having one copy of our image now in our visual cortex, we might have 16 copies of our image, each version of a different filter. You can also imagine like Photoshop, where you would apply different filters to your image, and you'd have each of those as a different layer of your image in some ways. And that's what we're doing here is we're stacking these feature maps up here. So originally we might start with a grayscale image. More often we'll start it with RGB image, so we'll actually have 3 different color channels here. And then we'll apply this filter to all 3 channels simultaneously, and we'll go up here and we'll actually apply different filters, and each of these layers will be a different copy of our image with a different filter applied here. And then we'll apply this filter again with different copies here. But here, rather than having an RGB color layer or just a single layer, we'll apply the filter to multiple layers. So this filter is actually applied to all the layers of the previous image. So we might start with an image, input image that is 28 pixels by 28 pixels by 3 pixels tall for our RGB, and then we might apply 16 different filters. So our resulting value is maybe an image that's 28 pixels by 28 pixels by 16 different filtered versions of this convoluted value images of that. And then our next set of features we might have, again, 28 by 28 pixels, but we might have 8 different filters applied, but they'll be applied to build more complex representations based on these values here. So this talks about a little bit about this, and again, you don't have to go over the math of this too much. We do want to look a little bit at the TensorFlow, or how this is set up, not necessarily in TensorFlow, but in Karis. So I'm going to skip over some of this TensorFlow stuff here and get down to here where we're going to do this in Karis. And I actually think it's easier to see in this image. Okay, so we've read in our data, we've got our data ready to go for our image, and then we have 3 different types, or a couple different types of layers. So we have a convolutional layer. This is our normal filter layer, and this is how we say a convolutional 2D filter, a con 2D. We say how many, or the size of the filter is 3 by 3. The activation rule here we're going to use, and these are our rectified linear unit, our modified version of the linear unit. And then we can specify, this is the main thing we do, is specify how many filters, how many different types of filters, and we're going to apply 16 filters here. The book shows it's a little more complicated here. Here's an example with 32 filters and a kernel size of 3 and a stride of 1, and the padding is the same here. Padding same means that we put 0 padding around it so that the resulting image is the same as the original image. So both of these do basically the same thing, although this one does 16 filters and this does 32 filters here. And again, you can give these names or not here, depending on how you have this set up. Okay, so those are convolutional layers. Another layer we commonly use is pooling layers. And these will be used to shrink our image down into a smaller size image. So we'll say a max pooling layer, and we'll say a pool by 2 by 2. And again, another way of saying that is saying it this way: a max pool 2D and a pool size of 2 here. 2 other layers we use. One is called a flattening layer, and that just converts a 2D layer into a 1D layer and flatten it out. And then the other one is this dense, and this is what we've been using before for our networks, and that's a fully connected network layer, and we usually use this at the end. So here's a common network here that we have set up. So we're going to start out with a 28 by 28 image, and now we're going to apply 8 3 by 3 filters to that image. So we're going to use a sequential network, and so all these are going to be stacked on top of each other. Our first layer we're going to add is a 2D layer, 8 kernels, and they're 3 by 3. And again, since this is the first one, we just have to specify what size the input is it's getting it from. So this will result in 28 again. It should say that the padding is the same here, and it's not. But assuming the padding is the same here, this will result in another 28 by 28 images. There'll actually be 8 different layers here for the 8 different filters. They're not all shown in this image. And then we're applying another layer of convolution 2D, 8 filters, 3 by 3. And so again, we're applying that again. Now we're going to shrink the image down some, and we're going to do max pooling 2 by 2. So I'll do this 2 by 2 filter across those things. So we'll go from a 28 by 28 image down to a 14 by 14 image, and it's applied to every layer here. So we last ended up with 8 layers here, and so we'll end up with 8 layers here also. Okay, and then we'll apply 16 layers filters here. They're just shown as they're just 15 different layers, and we'll apply them to every layer here. And again, we'll end up with this should keep the images the same size, 14 by 14, but now we'll have 16 of these layers rather than just 8 of these layers. Um, we generally, convolutional neural networks, the idea of convolutional neural networks are to detect more and more complicated features, and then you need less and less of them over time. So um, originally you might be detecting some edges here and edge detections, and then you'll be made more complicated things. You'll be putting edges together into circles and spheres and squares or different shapes or sections here. And then we'll do max pooling to reduce this. And so maybe we're trying to detect faces and we're starting to detect circles or eyes or stuff like that. So while there'll be lots of pixels here, there's not going to be that many faces on our image, so we can reduce our size down more and more. So here we'll reduce this, and this kind of forces our network to work with more features, but less pixel size of our image. And this is the standard way, and we'll see this more and more when we look at more complicated convolutional neural networks. Okay, so let's actually run this. So here's the questions and here's the code that you have to run. So you have to run this code and see how it works. So we're going to set up our network here. Again, convolutional 2D, padding is the same, input, and we have 8 input filters, another layer with 8 input filters, and then a max pooling filter, and then 16 filters, and then we're flattening it from 2D to 1D, and then we're doing a dense layer of 32 units, and then our output, our final dense layer is a softmax layer with 10 output layers. The output size is defined as 10 up here. We're going to print off a summary here so you can see. It's good to kind of watch the shape. So we start with a 28 by 28 image that's 8 different filters tall, and we do that again. We get another 28 by 28 8, and then we are going to do this max pooling, so our image size gets down to 14 by 14 by 8, and then we do some filtering, 14 by 14 by 16 filters. Then we flatten it. We end up with over 3,000 values in that, and then we apply a dense layer and then our output layer. One thing to watch is the total number of weights in our network. So the total number of weights in our network is 100,000, which might seem like a lot, but we will soon be getting up to networks with multiple millions of weights in these much deeper networks. And so 100,000 will train relatively quickly. When we get up to 16 million or so, we're going to run into longer training times. Here we're using, again, these are, and we'll talk more about these later, but some learning rate reduction and some early stopping rules that are put in place. And you can just leave these as be and not worry about them right now. And here is when we're actually going to train our networks. We're going to fit it to the data. We have our training data and our outputs. We have some testing data. We separated off here, and then we're running this for 10 epochs. So there are 37,000 images in here, and we're going to run it through 10 times, so it'll take a while to run here. I've already run this here. Each epoch here only took about 34 seconds, so this whole thing only took a couple minutes to run, which is really nice. Eventually, soon these will be taking an hour or so to run. I've actually run these for weeks at a time on bigger data sets and bigger images. So that one of the reasons we're using this very small data set is that it trains really fast. And then we can plot the history of it. And then we have the loss function, and we can see the loss function on the training data getting very small. And here we can watch the loss getting very, very small. And this, when the loss gets very small, it just means we have to use the loss to calculate how to change the weights. And when the loss gets really small, it means we're just not changing the weights very much here. And our accuracy is going up, but it's kind of plateauing here. Our training accuracy here. It's interesting here. We have probably overtrained this a little bit because our training accuracy is up here, but our validation, our accuracy is lower than that. But it's not going down too much. It's been both of them are pretty steady, and it also looks like having more training won't help very much because these are not necessarily rising. And if again, we could try training this for more epochs and see, but I don't think you'd get much better results. So your job then is to do some more changes to this network, try to experiment. And again, we'll be looking at lots of different structures for this network, but some things you can do, you could add more filters. So what if we do 16 filters here instead of 8 here? Or 32 filters here, or try different things. You can try different size filters. You could try 5 by 5 filters, 7 by 7 filters, 1 by 1 filters. Different options are available here. You can add more convolutional layers here. So here we have one convolutional layer. I could just copy that and add another convolutional layer here. I could add another max pooling layer here. I could copy that off and add another max, and then I can actually duplicate this. This is a common structure here where we double the size of the number of filters as we go each time. And we could run that. So here we could see what this network is. So here we've got 28 by 28 images, and we flatten it down to a 14 by 4, or not, we pull it down to a 14 by 14 image, and we pull that down further to a 7 by 7 image, and then we result. And again, this even though we've added more layers, we only have 68,000 parameters here because we've made this image, the final image is very small. It's 7 by 7 pixels and 32. So this is hopefully finding great, very high level result or features here. But I don't know, is that going to improve things or not? So you can try out a network like that if you want. Again, so your job is to, let's get down here, make 2 different changes, note the change and note the results on your things. And the last thing we want to do is have you do a Kaggle submission. This will create a file called CIS 6115 submission. Here it should be in, if you look in Colab, it should be right here. You may have to refresh this view, but you'll see this, and you can just download this to your computer, and then you can go to this Kaggle challenge here. You can upload it here. Let's see, let's do another submit a prediction here. Oh yeah, I just upload the file that I just downloaded from things. I can put a little description in here. Second permission for recording. I already submitted once to test this out, and I make the submission. It will upload the submission and complete it and give me some score here. So that's my score that it's getting currently. Okay, so that's your challenge for convolutional neural networks.